move like an interview and come back? Because I'll be
All the
recording another
problems that
one.
we haven't yet done, which are quite a few in number. And I think it would be best to go through them in reverse order. Okay, so let's go back to 11, according to my records. That's the last one that we haven't done yet. And for this one, we are going to have to reduce this to an equivalent capacitance step by step. Redrawing the circuit at each step in order to replacing each subset of series or parallel capacitors with its equivalent resistance, or capacitance rather. So anyway, we have to start out by finding some subset of these capacitors that are either in series or in parallel. Is there any such subset of capacitors here? What was that? Okay. Right, C3, C4, and C6 are in series with each other. Is C1 in series with C3? Okay, no, there's a junction here. Okay, there's a junction between them, but as far as you're concerned, they're not in series. Also, I want to ask, are C2 and C4 in parallel with each other? Okay, no, they're not. If they were in parallel, then these two, the tops would be directly connected and the bottoms would be directly connected, but they're not. Okay, C3 is getting in the way up here, and C6 is getting in the way down here. So just because two resistors or two capacitors are geometrically parallel to each other in a circuit diagram does not mean that they are connected in parallel electrically. So the first thing we have to do here, let's see, maybe I can scoot this thing over. Never mind. Let's just go ahead and redraw this with the with 3, 4, and 6 replaced by an equivalent capacitance, C3, 4, 6. So this is C1. Down here we have C2 and C5. And then our three capacitors in the rightmost branch get replaced by C3, 4, 6. Okay, so this is C2, C1, and C5. And what formula do we use to calculate the equivalent capacitance of the three series capacitors? Okay, right, the 1 over 1 over formula. So we've got 1 over the quantity 1 over C3 plus 1 over C4 plus plus 1 over C6, and so let's see, this is going to be 1 over 24 microfarads plus 1 over 12 microfarads plus 1 over 8 microfarads. And so I should probably try to do this in my head. But let's see. What I'm getting is 4 microfarads. right, so now we're going to carry this back here and redraw the circuit again. Is there any subset of capacitors in this network that are either in series or in parallel with each other? Okay, right. C2 and C346 are in parallel. Their tops are directly connected with nothing in between, and their bottoms are directly connected with nothing in between. Okay, and this is C, whoops, let's put the 2 first. This is C2, 3, 4, 6, and this is C5. Okay, and so how do you find the capacitance of capacitors in parallel? Yeah, you just add them together. So, and let me put this underneath. Our C2, 3, 4, 6 is going to be equal to C2 plus C3, 4, 6. C2 is 4 microfarads. C3, 4. Oh, I miswrote this. This subscript should be 3, 4, 6, not 3, 4, 5. Did everybody catch that? This I accidentally wrote as a 5, it's supposed to be a 6. So anyway, C346 is also 4 microfarads. That gives us a total of 8 microfarads. All right, and so now all we're left with is our single equivalent capacitance. C 1, 2, 3, 4, 5, 6. And this, once again, is a series connection. So we're going to use the 1 over formula. 1 over C1 plus 1 over C2, 3, 4, 6. Plus 1 over C5. That should give us our 2 microfarads. So let me try it out just to make sure. Our C1 is 5. Our C2, 3, 4, 6 is 8. And our C5 is 6. So adding the inverses and taking the inverse gives 2.03. Okay, so close enough. So now 19/20ths of the work is done. In part B, all we want is to find the total charge that flows out of the battery when this network is charged. So how do we find that? Okay. Right, well the capacitance is equal to Q over V, so Q is going to be equal to C times V. So Q 1, 2, 3, 4, 5, 6 is equal to C 1, 2, 3, 4, 5, 6 multiplied by delta V 1, 2, 3, 4, 5, 6. And our capacitance is 2.0 microfarads. What is our, well, it should be fairly clear that our voltage is 6 volts, okay, across the entire network. And so this is going to give us 12 microcoulombs for our total charge. Okay. Probably save this. We're moving on. Moving back. Is everybody done copying this, by the way? Okay. So, here we are trying to find the potential, the electric potential produced at the center of the rectangle by all these point charges together. Okay. The computer's starting to erase the stuff I write now. Here's our point P, where we're trying to determine the potential, and that disappears too. Okay. Well, okay. Now, a lot of you on the last exam, it seemed like you didn't know what variable name represented electric potential. So, when we're looking for electric potential, what letter is that? What letter represents electric potential?
U?
Well, U is electrical potential energy.
Okay.
Okay, but electrical potential is not the same as electrical potential energy. So what is electrical potential represented by? E? Oh, okay. It's V, all right? The way you can remember that is electrical potential is in units of volts, and volts starts with a V. So, electric field is represented by E. Electric potential is represented by V, and electric potential energy is represented by U elect. All right. Also, electric field is in units of newtons per coulomb or volts per meter. Electric potential is just in units of volts. And electrical potential energy is in units of joules. All right. So, you do need to memorize this, okay, because I'm not going to give you this stuff on the front page of the exam. But it seemed like a lot of you didn't know what letters were representing what quantities or what units those quantities had. So here we are looking for electric potential. That's V. All right, so this is our point P where we're trying to find the electrical potential. And electrical potential is a scalar. Okay. Electric field, on the other hand, is a vector. Okay, so when you add vectors together, it's the same old addition that you're used to. 2 plus 2 is 4. 6 plus 7 is 13. You don't have to worry about directions because the quantities don't have directions. If you're adding vectors, on the other hand, first you have to sketch the vectors, then you have to find their components, then you get the components of the resultant by adding the adding the x components to the vectors, adding the y components to the vectors. So what we're asked to find in this problem is a scalar, electric potential. So we don't have to worry about drawing arrows, we don't have to worry about finding components. All we have to do is add numbers together. The potential produced by any point charge is just kq over r. So this is going to be kq1 over r1 plus kq2 over r2 plus kq3 over r3 plus dot dot dot. Yeah, there are 6 total charges, okay? And we can factor out the k. But notice that we are not using the absolute value of q, okay? We are using the value of q with its sign, because a positive charge contributes positive potential at this point, and a negative charge contributes negative potential. So you cannot take the absolute value here. You only do that when you're determining the electric field. So we really don't want to have to go through and add up 6 different terms here. And we don't have to, because if you look at these charges, you can see that some of the potentials produced by various pairs of charges are going to cancel each other or balance each other, however you want to look at it. You're going to have plus something and minus something, and they're going to eliminate each other, and you won't have to worry about it. So looking at these various charges, which one of them, which pair, can you name one pair that will, whose potential contributions will eliminate each other?
3.
Okay, plus 3 and minus 3. Okay, yeah, well these are the same distance from point P, but they're opposite charges. So these two eliminate each other. Are there any other pairs? Okay, yeah, plus 5 and minus 5. Okay, this and this also eliminate each other. And of course, the only 2 that we have left are the 2 positive 7q charges, which are obviously not going to eliminate because they have the same sign. So the only thing that we have to worry about are these 2 charges. And they both are the same distance. Let me, I don't know, let's make this light blue. Okay, they're both the same distance from point P. Distance from point P to either one of these 7q charges. That didn't come out so well. It's hard to freehand this stuff sometimes. But this we'll call the distance r, and it's the same for both charges, but of course we're going to have to find it using trigonometry. So what's this leg of the triangle? Yeah, that's D. And what's this leg? Yeah, 1/2 D. So R R is equal to the square root of D squared plus D halves squared. And and that is just the square root of d squared plus a fourth d squared, which is going to be 5/4 d squared. D is 0.13 meters. So when we take the square root,
Where did you get the 5/4 for D?
oh, okay, well, I may have gone too fast through that. When you square d over 2, you end up with d squared over 4. Does that make sense? So we're going from here to d squared plus d squared over 4. And then if we factor out the d squared, this leaves behind a 1. And this leaves behind a 1/4. So 1 plus 1/4 is 5/4. Does that make sense? Okay. But anyway, you wouldn't have to do that. You could just plug in the D and put it in your calculator. So we take our 5 divided by 4 times 0.13. That gives us, well, after we take the square root, that gives us 0.403 meters. Really?
Is there no
Oh, I see, okay. Yeah, you're right. Always forgetting to square things. Yeah, that's, actually, 0.145. Meters, all right. So now, we only have two charges contributing their potentials, and the two contributions are equal to each other. So we don't even need two terms, we only need one term. We'll just put a 2 in front of it. It's going to be 2 times K times positive 7Q divided by R. So K is 9 times 10 to the 9th. Newton meters squared per Coulomb squared. We've got 7 multiplying by Q, which is 9 times 10 to the minus, what is micro? 10 to the minus what? Okay, yeah, 10 to the minus 6. Okay. That should give us our 7.8 times 10 to the 6 volts. But let me just check. Yeah. That comes out. All right. And so that was part A. And now, hard work is done. Now we just have to calculate the work that we have to do on this negative point charge to bring it in from infinity and place it right there at point P. And so, how do you find that? Well, I'll give you a hint. It's the same thing as the potential energy charge when we place it at that point. So if you know the potential at a certain point, and you want to find the potential energy of a probe charge located at that point, how do you calculate it? Well, work is equal to U elect, and U elect is equal to Q times V. All right, so now that you have the potential, all you have to do is multiply by the charge, and this is the probe charge. I guess I should specify that. Let's give this, let's call this Q probe. Okay, so Q probe is our negative 2 times 10 to the minus 6 coulombs. V is 7.8 times 10 to the 6th. And that will give us our negative 15.6 joules. So once you've found the potential, all the work is done. Does anybody need more time to copy this? All right. Problem 9. Oh, we did problem 9 already, didn't we? That brings us back to the standing wave problem. All right, so we've got this string tied to the ceiling with a hanging mass on it. Here's the ceiling. Here's the string. The mass is here. This we'll call M hang. And we want it to vibrate with 3 loops of a standing wave. So that's going to look like this. Roughly. Okay. So for a standing wave, there are only certain allowed wavelengths. And the formula for the allowed wavelengths is lambda sub m is equal to 2L over m, where m is equal to one of the natural numbers, 1, 2, 3, 4, etc. And this happens to be equal to 2 loops. All right. M is the number of antinodes, or loops, in other words. And so, I guess, well, I shouldn't say that lambda sub m is equal to 2 loops. I should say that it's equal to the length of 2 loops. So, if I have 3 loops on this string, what fraction of the string's total length is occupied by 1 wavelength? Right, 2/3. This right here is lambda sub 3. So our value of n is 3. Since m is the number of loops. So n is equal to 3, and we can say that lambda sub 3 is equal to 2/3 L. That's right. Okay, that should be a 3, not that one. Okay, this is 2/3 times our length of 1.10 meters. And that gives me 0.733 meters. So now we need to know the frequency. We know the wavelength of the wave. How do we find its frequency? Well, we can find the frequency from the fundamental relationship for waves. V is equal to F lambda, which means that F is equal to V over lambda. This is the frequency of the third harmonic, so we'll call this F sub 3, and this is lambda sub 3. And V represents the speed of the wave. Well, we don't know the speed, we're not given that, so how can we calculate it? Okay, right, for a string wave, the speed of the wave is given by the square root of T sub s over mu. All right, T sub s represents the tension in the string, and mu represents the mass per unit length of the string. So how do we find the tension in the string? Well, it's just the weight of the hanging mass, all right? That's going to be m hang times g. And, well, mu is given to us. So, let's go ahead and calculate this. We've got our 5.5 kilogram mass. We're multiplying by 9.8 meters per second squared. Mu is, oh, we didn't calculate mu yet. What expression can I substitute for mu? How would you find the mass per unit length of the string? Yeah, well, it's just the mass of the string divided by its length. Mass per unit length is mass divided by length. We take the mass of the string, which is 11 grams or 0.011 kilograms, and divide by its total length, which is 1.1 meters. And plugging all this into our calculators, 5.5 times 9.8 divided by 0.011 times times 1.1. All to 1/2 power, I'm getting 73.4 meters per second. And so, taking that and plugging it in here, we end up with 73.4 meters per second divided by 0.733 meters. And that should give us about 110 hertz. And that looks about right. something's up here. Oh, I know what I did. I looked over this and I knew I was missing something. The total length of the string is 1.1 meters, but it's tied 1.00 meters from the ceiling. So actually L is not the total length of the string, L is the active length. So let's see, we've got 2/3 L, which is 2/3 times 1.0 meters, which is 0.667 meters. And so we put this down here, 0.667 meters. And, no, wait a minute, I can't do that. 73.4 divided by 0.667 is, 110. So because we have two different L's in this problem, we really need to give these two different subscripts. This L, without a subscript, represents the active length of the string. That's the part of the string that's vibrating. When we calculate the mass per unit length of the string, we divide the mass of the string by its total length, which is not equal to the active length in this case. It's a little bit longer. So we'll call this L string to distinguish it from the active length. This is the total length of the string, which is our 1.1 meters. Okay? So, yeah, I looked for that and I just couldn't find it somehow. All right. So that brings us, well, let's save this before we forget. And maybe this would be a good time to return graded stuff. Like I said, the most important thing is the exam. Is Chad Wertz here? Bryce Lovett? Yeah, please start walking towards me as soon as I announce your name. That'll take up less time. Okay, Taylor Fitzgerald. Lizzie Winkler. Drew Mack. Tyler Jeffcoat. Kristen Ladis. Samantha Rowe. Michelle Veronin. Mallory Dyke. Joey Fisher. Wes Emanuel. Adrian Maples. Ovais Mohammed. Ashley Valentin. Kimberly Level. Monica Lewis. Holly Brown. Oh, Kristen, I have it's just your exam. There it is. Brittany Hudson. Christian DeVira. Adam McGeever. John Reinertson? Huh? Oh, I'm sorry, I can't give it to you. Oh, he is? Oh, okay. Where exactly?
Where that water bottle is.
Okay. Evan Ward? Joey Luizo? Christian Miller? Misty Hartman? Which is pulled down and then released from rest. And yeah, it's pulled downward 3.5 centimeters from its equilibrium position and released from rest. So this is what the initial situation looks like. It's down here. And here's the hand pulling it down. And then it's released from rest and bounces up and down. Speed through equilibrium of 3.42 meters per second. So let's draw that too. Here it is back in its equilibrium position, but now it has a speed of 3.42 meters per second. So we want to calculate the magnitudes of displacement and velocity at a given clock reading. If we want any quantity at a particular clock reading, we're probably going to have to use the position function and or velocity and or acceleration functions, which are all sinusoidal. X of t is given by a times the cosine of omega t. And this can also be written as a times the cosine of 2 pi over capital T times little t. We already know the value of little t. Now all we have to do is figure out the values of capital A and capital T. So first of all, what is the value of capital A? You remember what capital A represents? Yes, it's the amplitude. And so what's the amplitude in this problem? Well, it's just the maximum displacement from equilibrium. All right, if this thing is released from rest, this distance from equilibrium, then this is the amplitude. So that is simply our 13.5 centimeters. Actually, well, our answer is in meters, so let's convert this to meters first. And what about capital T? What does that represent? Yes, it's the period, the time required for one cycle, one complete cycle. And for a simple harmonic oscillator, that's given by the square root of m divided by k. So m is our 0.85 kilograms. K is, rats. Let's see. Oh, right, we're, okay. given the equilibrium speed. Let's start this over again. The equilibrium speed is V max. And that's given by omega times A, or and omega is just the square root of K over M. So this would be the square root of K over M times A. And we're trying to solve for oh, no, I don't need the spring constant. What I need is the period. Or actually, let's just go for omega. Let's just go for omega. Okay, omega is going to be equal to V max over A. Our V max is our speed at which we're passing through equilibrium, which is 3.42